Yes, so let me try.
Okay. Well, welcome everyone to the very first session of the Electro Week and Beyond the Standard Model session. And our first speaker for today is Shigeki Hirose, and he's going to talk to us about measurements and searches for the Higgs boson production involving fermion couplings with the Atlas detector. So take it away.
Yes, so do you see the full screen or the presenter's mode?
I think full screen would be better, yeah.
Okay, so is it fine?
Yes, this looks good, yep.
Okay, so let me start my talk about, let me change the, here. So today I'm going to introduce a little bit about the recent measurement and the searches of the Higgs boson production involving fermion couplings from the Atlas. So as you know, the Atlas experiment is one of the experiments carried out using the Large Hadron Collider, or LHC. And our detector, as shown here, is located at one of the proton-proton collision points. And this detector is a complex of the inner detector dedicated to finding charged particles, and the calorimeter to detect and also measure the energies of the electromagnetic or hadronic objects, and then the muon detector located outermost layer of the Atlas detector. And then this plot shows the total integrated luminosity collected over the time of the period, so-called round 2, starting in 2015 through 18. And in total, we collected 140 inverse femtoband of the data with the data taking efficiency of greater than 90%. At 13 TeV. And so that means that our data is by a factor of 5.6 more than what was collected in round 1 at 7 or 8 TeV. And these four diagrams show the main production processes of the Higgs boson at LHC. The gluon-gluon fusion has the largest cross-section, and then going towards the right, BBF and BH and TTH has smaller, but still significant cross-sections. And in total, the Higgs production cross-section is 55 picoband at 13 TeV. That means that our data taken through round 2 contains equivalently 80 million Higgs bosons. Such a large statistics allows us to try measuring kinematics of the Higgs productions. And to do that, we use the framework of simplified template cross-section, or STXS. That is a kind of framework for the differential cross-section measurement using the predefined binning based on kinematics such as the Higgs boson PT, number of jets, and so on. Also, we can try measuring more challenging or rare processes. And today, I'm going to cover these topics. So first three are related to the Higgs BB decays, and the latter two are related to rare processes, including the lighter leptons. So for the measurement of Higgs BB, we usually use the BH process, because then we can utilize the existence of leptonically decaying weak bosons to reduce background. These two plots shows the mass distribution for the Higgs boson candidate. This is based on the kind of standard method, and this is their measurement, so-called boosted measurement, by requiring the existence of a single large R jet containing two B jets. In both cases, we can see a clear signal contributions around 125 GeV. Actually, the significance is already 7 sigma, so this is a kind of well-established channel. And of course, we try the STXS measurement for several bins of vector boson PT. Then also we can try accessing to the different phase space by using the different production processes. And these two plots shows the results targeting the BBF production. The first result is we call photon tagged measurement by requiring the existence of energetic isolated photons in addition to four jets representing the BBF jet and also Higgs decay products. Existence of such a high energy photon allows us to reduce the background to some extent by utilizing a dedicated special trigger. We also try the measuring this process more inclusively with targeting the boosted Higgs exceeding the PT of 150 GeV. In this measurement, we intentionally vetoed the high energy photon to assure orthogonality to the previous measurement. And these mass distributions vaguely show the signal contributions around 125 GeV. And by combining them, the signal strength or the number of observed signal relative to the standard model expectation is measured like this, with the significance of nearly 3 sigma. And we also do the more inclusive measurement targeting the very high PT Higgs productions. For that, we choose events with at least one larger jet containing two B-tagged subjets. This plot shows the definition of the regions. So first, we check the reading larger jet, and then if this larger jet has two B-tagged subjets, we define the signal region of the reading. If not, then we try to check the sub-reading larger jet, and if it satisfies the requirement, the signal region is defined as SR sub-reading. Also, we can use events having a larger jet, but without any beta-tagged subject for the validation. As expected, the main background is from multi-jet background, so its shape is checked using the validation region. Also, the jet mass reconstruction is important for this analysis, so it is validated using the vector bosons or top resonances as shown here in the validation region. And here, in this plot, the multi-jet contribution is already subtracted. And these two plots shows the fit results to the signal regions. And you can see some signal contribution around 125 GeV. And we measured the cross-section normalized by the standard model expectation for a few beams of the Higgs boson PT, as you can see here. So what is interesting is that we start to measure the very high PT regions exceeding 1 TeV, although still the uncertainty is large. So this is one example of the measurement of the cross-section result from the cross-section measurement. And so far, statistical uncertainty is dominant, while the main experimental uncertainties arise from the expansion of the jet mass resolution. So last topic related to Higgs PB is targeting the TTH production. This process is of course interesting because we can directly measure top-quark coupling. And for that, we tried several different channels as summarized here. And then this process, TTH, is already observed exceeding 5 sigma. And today, I'm going to introduce a new result, updated results of the TTH measurement using Higgs PB using the full data set of LAN2, meaning that the statistics is increased by a factor of 4. On this measurement, of course, this is a very challenging measurement because the final state is composed of a lot of jets. And already, as you can see here, the previous measurement was systematically dominated. So the background modeling, including the top-quark, is the key of this measurement. To do that, a lot of signal regions are defined as well as the control regions as summarized in this table, but I don't want to go into details of this plot. And then we successfully control the background. And also, this final signal definition of the signal regions targets the ST-XS measurements. And this is the summary of the measured signal strength, where one means the standard model expectation. So in the for all regions and also the inclusive results, everything was consistent with 1. And this plot shows the VDT output distributions for the most sensitive region, and you can see some signal contribution here. The result is as shown here. So the observed significance was 1.3 sigma, which is lower than the expectation, but still within 2 sigma. And the systematic uncertainties were dominated by the modeling of TT bar events having additional digits. And then moving on to the leptonic final states. So here we can expect more cleaner signature because of absence of the hadronic interactions in the final states. And this is just one example from Higgs to tau measurement, and you can see some significant signals around 125 GeV. Already, this is well established with roughly 20% of the precision, and this is and we are now trying to improve this result using the full dataset of LAN2. And at the same time, we can try more rare processes containing light leptons, such as Higgs mu. Although the branching fraction is very small, but the final state is very clean, that may realize observing those processes at LHC. This is so Higgs mu is quite interesting channel because we can investigate the Yukawa coupling in the second generation of the fermion. And although the final state is clean, but we have to copy the overwhelming background from the Dorelian process. So first, we try improving the mass resolution by recovering FSR photons emitted from the muon. And in order to separate the signals from the background efficiently, event categorizations was done using the VDT output, and in total, 20 exclusive signal regions were defined. And this plot shows the fitted results to the signal regions. And at a glance, the distribution is fully consistent with the background expectation. But by subtracting the background contributions, you can see some signal contributions around 125 GeV. The measured result is summarized here with the observed significance of 2 sigma. And together with CMS, evidence of the Higgs mu was observed for the first time, including the expected significance. So the last topic is the brand new result of the Higgs boson decaying into 2 leptons and additional photon. And this is only a one representative diagram. And so this process is via a loop. And in this analysis, the measurement is done with requiring the dilepton mass less than 30 TeV. So in this mass region, the contribution from virtual photon is dominant. Using this channel, we can prove a coupling between the Higgs boson and other particles appearing in the loop. To do that, 9 signal regions were defined depending on the flavor of the light leptons or jet kinematics. And the main background is from non-resonant LL gamma, as shown in this mass distribution, and this corresponding contribution is shown by green. So this background is controlled by by determining the normalization in the fit, while its shape is checked using the control region. So, and this is the summary of the result, showing the cross-section times branching fraction normalized by the standard model expectation. So, so for the results from all 9 regions are consistent with 1, including the inclusive results. And this plot shows the mass distribution, and as you can see, a signal peak around 125 GeV. The result is shown here, and observed significance reached 3 sigma. So this is the first evidence of this channel. So for the summary, many analyses using the full dataset of run 2 were complete, and thanks to such a huge statistics, precision measurements for the Yukawa coupling was possible, and also in particular, third generation fermion coupling has been all observed. And the results are getting more important in the STXS measurement, although I didn't mention in quite detail today. And rare processes such as Higgs mu, Higgs LL gamma become possible. And not only that, but also other few interesting analyses are still ongoing, as well as the combination of the full measurements. And towards run 3 operation, starting within 1 year, the data size will be doubled. So this is definitely a good opportunity to more precisely understand the Higgs properties. So that's it.
Thank you, Shigeki, for the summary of these atlas results. Are there questions, comments? And please raise your hand. Go ahead, Henning.
Hi, thanks for the overview. I have a question on your TT Higgs analysis where the Higgs decays to BB. So you showed these STXS spin measurements, I think, yeah, right here. So my question concerns T Higgs and TW Higgs channels. So how to understand here this mu TT Higgs? Is this really TT Higgs or a combination with T Higgs and TW Higgs?
So I mean, how the contribution from T Higgs and the TW Higgs are treated?
Yeah, do they go in here or do you separate them, or how are they treated?
Okay, so in my understanding, it's separated. So and then estimated using the Monte Carlo.
Okay, so but for this you rely on standard model kinematics, I assume.
Yes.
Okay, so but you didn't perform any checks that for any BSM models which can change the kinematics.
Sorry for that. I don't have the exact answer. Sorry.
Okay, no worries. I was just curious because in some BSM models, obviously the kinematics can be changed, and then it might be questionable if your separation still works. But yeah, okay, thanks.
Okay, thank you. We have time for one more question, if there is a question. Okay, if not, thanks again, Shigeki.
Thank you very much.
Now we go to VINAYA, who will tell us about measurements of CP structure in Higgs boson decays to pair of tau leptons at CMS. VINAYA, can you please share your slides?
Sure, 1 minute.
Okay, and while you are sharing, just a reminder, you have 15 minutes for the presentation.
Can you see the slides?
Yeah, we can see the slides. Yeah, that's good now.
Okay. Hi all. So today I'm going to talk about the measurement of CP structure of Higgs tau Yukawa coupling. Here I'm giving a couple of motivation to this analysis. So according the standard model Higgs is CP even. We can there are some studies which happened for this Higgs 2 vector boson, but there the gauge boson CP odd enters only for the higher order terms. But in the Higgs 2 fermion coupling, we can see the CP odd couplings at already at the tree level, and this analysis Higgs 2 tau events which the measurements are more close to model independent, and the results showed in these slides are from the CMS bus Higgs 20006, and the analysis performed for full run 2 data in the channels for the mu tau and fully hard dihadronic channels. So in this slide, I'm showing the Lagrangian for Yukawa Lagrangian. So here you can see the two terms for with the Higgs coupled with the two taus. So the first term is give the pure CP even state, and the second term is give the pure CP odd nature. So and I define a mixing angle phi tau tau, which defined as like tan phi tau equal to the ratio of these couplings. So when this phi tau tau becomes 0, we'll get the pure CP even. When it become pi by 2, we'll get the pure CP odd states. When you compute the differential cross section, you may get the cross section with it's proportional to this cosine of this phi CP with the phase of these two phi tau tau. So this phi CP is basically the angle between the tau lepton decay plane in the Higgs boson rest frame. So by measuring this phi CP, can probe the mixing angle phi tau to which have the advantage that measurement can be interpreted as model independently. So in the next few slides, I will talk about how this phi CP distribution reconstructed. So first, the tau leptons we know decays to leptons and harmoniously. So in the right pie, you can see the branching fraction for different decay modes of taus. There are separate methods to construct the angle between these two lepton decay planes for each decay mode. So for suppose for one prong decay, such as only one charged particle like muon or pi plus, we constructed the decay plane with respect to the by using the charged particle momentum and the back parameter. When if there is at least one pi 0 is there, so the decay plane can be constructed from the momenta of charge and neutral pions. So here I'm describing this the three methods to construct the decay planes for decay planes for each decay mode. So you can see in these figures, these three figures, you can see that how this phi CP angle related to with the decay planes. In the first method, the impact parameter. So we obtain this three-dimensional IP vector from by parameters in the electrical trajectory. Once you have the impact parameter and the charge momentum vector, charge particle momentum vector, where you boost this charge momentum vector and the impact parameter to the pi plus pi minus 0 momentum frame. So in that, so these all three diagrams in this 0 momentum frame. So from this, you can easily calculate this phi CP angle by using this equation. In another, for the other method, the neutral pion momenta method, instead of IP vector, we have this pi 0 momenta. So we can construct the decay plane with the pi 0 and pi plus pi 0 and the charge form momentum vectors. But in the special case like A1 3 prong, in here we have three charged pions. So what we do is we select oppositely charged this pi plus and pi minus with a which is close to the invariant mass of the rho 0 meson. And this treat the in this pair we treat the pi with the opposite charge to the tau as a neutral pion, and another pi we used for the constructing the 0 momentum frame. And for the mixed method, it is basically in one hand we use the impact parameter, in another hand we use this pi 0 for the neutral pion method. So in this table, I'm summarizing the whole method used for to construct this phi CP for the different decay modes. And the right, you can see the phi CP distribution in the generator level for the CP even and CP odd and the maximum mixing and with the Z boson. And move to the analysis. So the event selection and the background estimation and the other corrections are outlined in the past. And but in this analysis, we also included some special methods to get a better performance. One is vertex refitting, which is actually we instead of the standard primary vertex, we used a new refitted vertex which exclude the tau tracks from the tau tracks and also apply beam support constraints, which will give an improvement to for this IP method. And we used a MVA decay mode identification. In the CMS, the tau decay modes are identified using the HPS decay modes. But we here in this analysis, we used a decay mode which is obtained from the MVA multivariate analysis. So the new choice of decay modes improve the sensitivity up to 20%, expected sensitivity to 20%. And we also used a background flattening and symmetrization to reduce the structural friction, which I will come in the next slide. So the extraction of signal and background events from is performed using this machine learning techniques. For the mu-tau case, we use the neural network, and for the harmonic dipole case, we use this BDT one. And once we get this 5CP distribution, which from using this 5CP distribution, we extract this phi tau by using maximum likelihood fit. So here is the discriminant to go through the to fit this phi tau. So here this this discriminant is basically the 5CP distribution of the events in for a different windows of increasing order of MVS score, which you can see that 0 to 0.7 and 0.7 to 0.8, and these are the MVS score. And each window you can get this 5CP distribution, and you can see that it is before there were in the left hand you can see that backgrounds are randomly fluctuated highly, and here we ordered in a way looks smoother, background looks smoother. So this is by using by the flattening of the backgrounds. I mean this flattening is only applied for the genuine tau backgrounds, and symmetrization is applied for the jet fakes backgrounds. And in the downside, you can see all the backgrounds are symmetrized. This is because here it is the IP method. So when when this IP method performed, there was a high smearing in the primary vertex, so which shows this kind of distribution. So we also symmetrize the background as like this. And final, the estimation of phi tau by using this combined fit. So for the combined fit, use this likelihood function with the parameter of signals, Higgs boson signal strength, and the CP mixing angle phi tau, and considering the nuisance parameters. So when we using maximum likelihood, we obtain this. We draw this phi tau with respect to the negative log likelihood. So you can see this blue line is the expected one, and the red one is for the observed case. So with the mean of 4 degree and uncertainty of 17 degree in the 1 sigma confidence level. So similarly, in the down left, I also show a dedicated 2D scan performed for the Yukawa coupling for the CP1 and CP0. So this measurement also consistent with the standard mode of production within the 68% confidence level. So by taking all this, let me summarize the results. So the presented full run-to result for the measurement of CP structure of Yukawa interaction between the Higgs boson and the tau leptons, and the current measurement performance on the mu tau and harmonic tau channels hadronic dipole channels. The observed results of CP mixing angle at the 68% confidence levels is shown in here. And from this, a pure pseudoscalar boson excluded at 3.2 sigma. And the results are consistent with the standard model, and some further studies are going on, which will go for publication for later. Okay, that's all from my side.
Okay, great. Thank you, Vinaya. Are there questions, comments? Please raise your hand if there is a question. In the meantime, maybe I'll ask a quick question here on this slide. When this 2 degrees Celsius bean by bean, essentially, no, sorry, on the slide 10, the next one. So this is essentially the Monte Carlo statistical uncertainty, or what is this bean by bean?
This is basically for that background uncertainty, which is the background with for each bean in the flattened bean uncertainty.
Okay, I see. Henning, go ahead. Henning, if you are speaking, we cannot hear you. All right, maybe let's see if are there any other questions while we wait for Henning? Okay, seems not. Vinay, I had one more question actually on slide when you show all the tau decay reconstruction modes. If you go to one more, yeah, here. So essentially for the hadronic tau, so you consider only 1-prong and 3-prong decays, or also no, you do include the neutral pion, is the, so as you say in the slide here.
Yeah. So the row meson basically then. Yeah.
Okay, thank you. Okay, let's see if Henning is, can you say something? If not, we do have to take this offline. Well, actually, Henning is the next speaker, but let's see. All right, thanks.
Can you hear me?
Yeah, we can hear you now. Did you have a question?
Ah, nice. Okay, great. Okay. Then I try to continue.
Okay, but did you have a question to this talk, or?
Yeah, right. I had a question, if I'm still allowed. So I had a question to the likelihood on page 9, I think.
Vinaya, can you go to page 9, please?
Okay.
Vinaya.
I can also say it without looking at the slide. So my question was just if there's any, if you could think of any method to actually constrain the sign of the top-Yukawa coupling, the tau-Yukawa coupling.
Sorry, let me. I thought that I had to close the window. Let me share one more time. What was your question, Emily?
Yes, on slide 9, you showed this 2D likelihood, and obviously there's a symmetry between, so there's a sign symmetry, so yt going to minus y tau. And do you see any possibility to constrain the sign of the tau-Yukawa coupling?
Which sign you're talking about? This?
Of this kappa t, so kappa tau. So kappa tau you can could be 1 or minus 1.
But what we excluded from this is the kappa tau theta is 0. So
yes.
Yeah.
But I'm just asking if you see any possibility to.
No, that's I'm not sure. I don't know.
Okay.
Okay, thanks again, Vinaya. Now we go to Henning, who will tell us about the indirect CP probes of Higgs top-quark interactions and the LHC constraints.
Okay, let me stop here.
Thank you. Yeah.
Okay, can you see my slides?
Yeah, we can see your slides.
Okay, nice. Okay, so then just give me a second, and then I will start. Okay, so I will talk not about the tau Yukawa coupling, but about the top Yukawa coupling and indirect CP probes of it. And I will discuss current LHC constraints and future opportunities. So let me start with my introduction. So why do we want to learn about the CP nature of the Higgs boson? So obviously, it's well known that for creating the baryon asymmetry of the universe, the CP violation is needed, and the standard model CP violation is not sufficient. So one possibility to add additional CP violation is to extending the Higgs sector in some way, which introduces CP violation, and then the standard model like Higgs boson could be a CP at mixed state. And as we already heard in the previous talk, the Higgs fermion fermion couplings are especially interesting in this respect because they have the largest CP violation in both BSM series is actually predicted in this fermion fermion couplings. So in this talk, I will focus on the Higgs top-quark coupling. And in general, CP violation in the Higgs sector can be constrained by either demanding the successful explanation of the baryon asymmetry, electric dipole measurements, or collider constraints. Here, I will focus only on the collider constraints and then assess LHC constraints and CP violating top-quark coupling and discuss future opportunities. So we performed our study in an effective model with an effective top Yukawa Lagrangian, where you see here, this is a standard model coupling in which we modify by a modifier CT. And then we have a CP odd coupling modified, which is parameterized by the CT tilde. So this is exactly the same as in the previous talk, where we had a kappa tau and a kappa tau tilde. So here we just call it CT and CT tilde. Then the modified top Yukawa coupling affects different processes. So first of all, there's top associated Higgs production, which is channels TT Higgs, T Higgs, and TW Higgs. Then there's set associated Higgs production via loop effects and also via loop effects gluon fusion and Higgs gamma gamma. In our FET, we also have additional free parameters, which are CV, which rescales the HVV couplings, and also T Higgs and TW Higgs depend on this. And we also can allow for additional new physics in gluon fusion and Higgs gamma gamma independently of the modification of the top-quark coupling. And this we parameterized by a modifier kappa G and kappa gamma, which then effectively enables us to remove either the gluon fusion constraints or the Higgs gamma gamma constraints. We did not include any CP odd HVV operators, and
is it? I think we lost Henning. Is it just me who cannot hear him, or others can't hear him as well?
I can't hear him.
Okay. Henning, if you can hear us, we've lost you. Okay, yeah, it seems. Let's maybe give him 1 minute to see if he can fix this. I think he is reconnecting. Henning, can you hear us?
yes, can you hear me?
Yeah, we can hear you. But we just lost you again, it seems. Maybe what we can do is perhaps we can go to the next presentation while you try to fix your microphone issue. Yeah, maybe let's do that, and then we will come back to you, Henning. Yeah. All right, Dongshuo, are you connected? Dongshuo, can you hear us? I think we will go with your presentation now, and it's on measurement of the Higgs boson in decays to bosons using the Atlas detector. Please share your slides.
Hi.
Hi, it was Dongshuo, can you hear us?
I think I'm back.
Ah,
So,
you are back. Well, considering we are not getting any response from the next speaker, if you are certain,
okay.
you are certain that you fix your issue, I think we can continue with you. Yeah,
yeah, I'm really sorry, but some of my internet connection is a bit unstable at the moment. Normally, I don't have any issues at all. But
sure.
Shall I continue or?
Yeah. Now it seems to be good. Please continue.
Okay. So I will just okay. Okay, so yeah, I wanted to discuss the global fit. So for the experimental input, we use all relevant Higgs measurements, so especially Higgs thickness measurements, statics, STXS measurements, targeting the PT shape of the Higgs. But we did not include any dedicated experimental top-quark CP analysis because they are difficult to reinterpret in a different model. If available, we also included all uncertainty correlations, and for the theory input, we derived fit formulas for all observables using MapGraphs. And we considered 4 different models. Here we'll only discuss 2. The most constrained one, where only CT and CT tilde are treated as free parameters, and fluent fusion rate and the Higgs gamma rate is calculated as a function of CT and CT tilde. And then the 5-dimensional fit, where CT, CT tilde, ZV, kappa G, and kappa gamma are treated as free parameters. And then we performed the chi-square fit using Higgs signals. I will just shortly discuss the theory input for top-associated Higgs production. So here you see the combined signal strength of all three channels. And on the gray ellipse, it's equal to the standard model. The standard model is here this cross, this is the CT and CT tilde plane. And you see that if you go outside of this ellipsis, the signal strength increases, and inside it decreases. And then the red ellipsis shows you the kappa gamma. So the fluent fusion modification of the fluent fusion rate, and it's equal to 1 on this ellipsis stretching to the left. And in white, there's a Higgs gamma constraint, which is basically almost a vertical line here. So we remember the shapes that will then become important later, but I also want to point out that TT Higgs and T Higgs are difficult to disentangle experimentally, so normally a combination of both is measured. So here are the fit results for the most constrained fit, where CT and CT tilde are free, and you see that here, so you see delta chi squared in the CT tilde plane and the 1, 2, and 3 sigma ellipses. And you see that at 1 sigma, CT tilde is quite constrained to be within 0.3. Plus minus 0.3. And the form of the ellipsis is basically described by this fluent fusion constraint. So remember this red ellipsis from the previous slide, which is then cut off to the left by the Higgs gamma constraints, which can be, so Higgs gamma can of course be measured independently with fluent fusion. We now go to the most general model where kappa gamma and kappa G are free. Basically the Higgs gamma and fluent fusion constraints are removed. And we go basically to this ellipsis of the combined thickness strengths we see. So the CT tilde allowed range is much enlarged to 1.1. And only the left-hand side of the ellipsis is disfavored because there are some measurements which are actually sensitive here, constrain the left-hand side. So these are set Higgs measurements and some top-associated Higgs measurements in the 2 lepton category. So we still see that there's still significant CP couplings allowed in the 5D model. So obvious question is how to improve these constraints in the future. Of course, one could include more kinematic information. This is, for example, the Atlas and CMS studies, the dedicated ones did. and they use kinematic or all informable kinematic information, but there's a comparably high model dependence because you have to train a BDT or something. And another way is to construct CP-odd observables, like we heard before for the Higgs to tau-tau. But this is easy to interpret, but it's experimentally difficult for top-associated Higgs production. And then, of course, we can also use inclusive measurements, like we did in our FIT. This has a comparably low model dependence, but deviations could also be caused by other BSM physics. And of course, we should pursue all approaches to exploit the complementarity. So I will just today discuss inclusive measurements in the future. So what could we do to constrain it? So the most promising candidate is, of course, improved T Higgs and TT Higgs measurements. And you see here the combined signal strength for T Higgs plus TT Higgs plus TW Higgs. And you see here plotted against CT tilde, and you see there's actually, the dependence is really flat, so a precise measurement of this quantity won't help you to constrain CT tilde any further. If instead we could disentangle T Higgs from the other two channels, so this is basically the ratio of T Higgs over TT Higgs plus TW Higgs, there's a dependence is visible, and a precise measurement of this quantity would allow us to constrain CT tilde. So this is actually what we did then. We did a protection study for the high Lumi LHC, and our goal was to measure the T Higgs cross-section in a model-independent way, which means that we want to measure it without any assumption on the CP character. So in the present study, we focus on Higgs to gamma-gamma, and we split events into two categories. One lepton category where all channels contribute, which we optimize for high TH fraction, and the two lepton category where only TT Higgs and TW Higgs contribute, which we then use basically as a control measurement for the first category. So let me just shortly discuss how we enhance the T Higgs fraction. So an obvious cut to separate T Higgs from TT Higgs is a cut on the rapidity difference of the leading B and the leading non-B chat. So here cutting in two, you see the two signals, so T Higgs in orange and TT Higgs in blue. They are nicely separated in this variable, but the point is, or the problem is that the TT Higgs shape actually depends quite strongly on the CP character of the Higgs. So here we see different CP hypotheses, and you see the different shapes. And if you run the numbers, you see that the TTH selection efficiency varies by 40% in the one lepton category for different CP hypotheses. So to actually use this as a measurement of T Higgs, we would need to put in an assumption on the Higgs CP character a priori, which is not what we want. If instead we use another observable, which is the geometric mean of the rapidities of the leading chat and the gamma-gamma system, we also see a nice separation, but there's a variation of the selection efficiency for TT Higgs is much smaller. It's lower than 2%, and this is actually what we want and what we use then. Running using then 3 inverse autobahn, we see that we can constrain the T Higgs signal strength to be below 2.21 at 95% confidence level assuming standard model data. This is 5 times stronger than the current strongest limit, and also stronger than the most optimistic projected high-lumen C limit. And then you see here basically the impact in our FIT. So this would be then the screen band which we add, which would constrain, which then allows to constrain the significant parameter space. So this brings me to my conclusions. So our initial question was, how well can one constrain a CP-odd component of the top-quark coupling using current measurements? We performed a global fit to all relevant LHC data. We used effective Lagrangian with generalized top-quark interaction. We included all relevant total and differential cross-section measurements. Our fit results show that there are strong constraints coming from fluid fusion and Higgs gamma-gamma, but sizable CP-odd coupling is allowed if we allow for new physics in these processes. A future disentanglement of TT Higgs and T Higgs could then help to further constrain the CP-odd character, and we need to ensure that measurements which we use in such fits do not rely on assumptions of the Higgs CP character. Thanks for your attention.
Great, thank you very much, Henning, for this nice talk. Are there questions and comments for Henning? Please raise your hands. maybe while we are waiting, if you go to, so essentially when you consider these different models, so I think if you go to those ellipses that you were showing for the global fit, I think it was slide 8, perhaps.
This one.
Yeah, this one. So if I understood correctly, for the left plot, you are calculating CT and CT tilde as a function of kappa photon and kappa gluon, kappa G, right? So they are calculated.
No, it's the other way around.
The other way around. Yeah, sorry, the other way around. Now, if you just allow it to be on the right plot now, just allowing it to be basically free, independent from each other. But what kind of models are we talking about here? I mean,
So obviously, this is so we are looking at this in an EFT perspective, where we have some operators which you fit independently. But obviously, you would need a new color particle to basically get to vary the gluon fusion rate, and you need a new charge particle for varying Higgs to gamma. And actually, actually, if you make a simple estimate, these particles, so if you go up, let's say, to CT tilde equal 1, these particles have to be quite light. So in a realistic model, these points are probably hard to realize, one has to say. But from an EFT perspective, obviously, you can fit the operators independently from each other.
Okay, I see. Interesting. And you mentioned something about constraints coming from electric dipole measurements. So I know this wasn't covered in your talk, but let's say how strong they are compared to.
They are really strong in comparison. This is so there's this bar C diagrams, especially contributing to the electric dipole the dipole moment of the electron. And these are really strong, so they narrow CT tilde down to, let's say, 0.001 or something like this. But there you, of course, rely on the assumption that all the other Yukawa couplings are standard model-like. So especially the electron Yukawa couplings, or in some sense you need to couple the Higgs to the electron. And if you put this coupling to 0, for example, then all these constraints vanish. And at least at the LHC, we will have no means to actually measure the electron Yukawa coupling. So there are always ways to come around these constraints. It's not nice, but again, this says that we need to exploit complementarity between different measurements.
Yes, yeah, makes sense, absolutely. Okay, thanks a lot, Henning, for this nice talk.
Sure, sorry for the internet problems.
No, it's fine. At the end, it worked out nicely. All right, now we go to Dongshuo Du, who will tell us about measurement of Higgs boson in decays to boson using the Atlas detector. I see he started already sharing the screen.
Can you hear me and see the slide?
Yeah, we can hear you and we can see the slides. Please go ahead. You have 15 minutes for the talk itself. Yeah.
Okay. Hello, I'm very glad to be here to give a talk. And my topic is about measurement of Higgs boson in decays to bosons using the Atlas detector. And next slide is outline. My talk mainly contains 4 parts. First, I will give an overview of Higgs physics in the diboson final states. Then I will show the Higgs mass measurement in the ZZ Dicke tunnels. And next, I will show the Higgs boson coefficient measurement, and mainly contain 2 parts. First is the ITS measurement in the A2W, A2ZZ, and A2 gamma Dicke tunnels. Then I will show the fiducial inclusive and differential coefficient measurement in the A2ZZ and A2 gamma Dicke tunnels. Lastly is the summary. And slide 3, you can see from the bottom right plot. For Higgs mass with about 125 GeV, A2BB is the most prolific decay, but this channel is very hard to observe. And for the branch ratio of A2ZZ to 4 lepton, the branch ratio is about 0.012%. And for the A2 gamma, the branch ratio is about 20 times larger than the A2ZZ to 4 lepton, and it's about 0.23%. And for the A2W to NU, the branch ratio is about 1%. And the final states from this tunnel are very sensitive and which can leave a clean signature in the other detector. And for the A2ZZ to 4 lepton, the final S will be larger than 2. And for the A2 gamma gamma, the final S will be about 5%. And for the these two channels are the most sensitive channels for observation. And for the A2 WW to a new which have a larger branch ratio compared to A2 gamma gamma and A2ZZ to 4 lepton. And it also have clean signatures with high background. So these three channels can provide a powerful tool for measuring the Higgs properties. Next slide is about the Higgs mass measurement. In this study, we are using the Forslund dataset at 13 TeV with integrated luminosity of about 139 inverse femtobar by using the A2ZZ to 4 lepton and 4 set of final states considered. 4 electron, 4 muon, and 2 electron and 2 muon. This channel is the best channel for Higgs mass measurement, and but the uncertainty of the mass depends on the mass resolution. So in order to improve the resolution, the following stuff we are used. First is the kinematic fit, the imaginary mass of the leading lepton pair to the boson mass. And the second is the final state relation. Photons are included in the mass computation, and we also consider the imaginary mass resolution of the for lepton system on a per event basis. And finally, we are using the for BDT beams to further distinguish signal from the background, and the results are extracted Y profile likelihood fit to 16 analysis categories, and left is the results. And we can see that the results from its final state is compatible with each other and also with the combined results. And the Higgs mass from combined fit is about 124.92 GeV plus minus 0.2 GeV. And on this plot, the error bar on the point is the total uncertainty, and the bracket is the systematic uncertainty. So we can see that this measurement is still statistically limited. And slide 5 is about the HTS. And the goal is HTS method is to improve the sensitivity of the measurement and also reduce their dependence on the theory. And for the high PD beams, they are more sensitive to the BSM effect. And the STX framework provides different states with varying degree of granularity. And the STX category units in beams of truth variables like PD Higgs, number of jets, and MGG in different production modes. Firstly is GGH production mode. It mainly contains GGF plus ZH with the hadronic decay, and then first split by PD Higgs, then split by number of jets and MGG, and second is electroweak QH production mode. It mainly contains VBF plus weights with V hadronic decay, and bottom is HTS binning for the weight and the TTH production mode, and for the weight, the V is leptonic decay. And the HTS were suited to combine different decay channels, and the Higgs boson properties measurement with 139 inverse femtobar for Higgs mass rapidity less than 2.5 in the following. And slide 6. First, I will introduce the A2WW analysis. Firstly, the solidity. This analysis using the Forslund dataset and the signal different fluid opposite charge leptons plus missing ET. And you can see from the middle right plot, it's the number of jet distribution at the precision level. And we can see that different thermal composition for different jet beams. So the events are split into 4 analysis categories based on number of jets. And for the GGF, 3 categories, they are cut-based analysis, and for the VBF, it is DNA-based analysis, and in this analysis, the main backgrounds are non-Reynolds, QQW, top and zero total, and for the GGF, these 3 backgrounds are normalized by control readings, and for the VBF, only top and zero total normalized by control reading, and on the bottom right plot is the MT distribution in the WW0Z control reading and top 0Z control reading on right. And for the fake background, they are normalized by data-driven fake factor method. And slide 7 is the ITS measured in the A2W tunnel. And this analysis is based on the reduced series 1.2 category to ensure sensitivity for measurements. And the analysis is split by 11 categories by PD Higgs, number of jets, and MGG. And in the recall level, there are total about 17 single rings are considered, and the control rings split similar to single rings. In total, 27 control rings are defined to control QQW, top, and zip total. And slide 8 is the result, left is the coupling result. And for the GGF in A2W channel, the cross-section is about 12.4 plus minus 1.5 picobar. And for the VBF in A2W channel, the cross-section is about 0.79 plus 0.19 minus 0.16 picobar. And from this plot, we can see that the results are compatible with standard model prediction within 1 sigma. And on the right is the ITS results. The results are extracted by profile lactic fit in 17 single rings plus 27 control rings. And in this plot, the error bar is the total uncertainty, and the green box is the statistical uncertainty, and the green box is the systematic uncertainty. And we can see that for the GGH uncertainty, they are limited both by certist and systematic uncertainty. And for the QQH, the uncertainty are limited by statistical uncertainty at the high MGG and high PTX region. And the results are compatible with standard model prediction with a p-value of 52%. And slide 9 is about the A2ZD to 4 lepton analysis. And this analysis has small branching ratio, but with the best final SOB ratio. And also have clean signature, and the final series can be fully reconstructed, and also have good mass resolution. In this study, we are using the Forslund data, and the signal are for leptons, and the background counting a reducible background for ZZ and the gamma star. This background are constrained with a data-driven technique. And for the reducible background with non-permanent lepton, they are estimated from data. And in this analysis, the multivariate discriminates using the neutral network are used to separate the GGF from the background, and also to separate different production modes for 1 and 2 jet reconstruction categories. And on the top is for lepton invariant mass distribution, and we can see clean picture here. And the next slide, slide 10. On the left is the cross-section measurement for the 4 main production modes. And in the plot, the error bar is the total uncertainty, and the bracket is the certist uncertainty. And on the top right here is the number factor for ZZ and TITS in different categories. And the inclusive A2ZZ production cross-section is about 1.34 plus minus about 0.12 picobar, and a good agreement with standard model prediction. And on the right is the ITS results. And we can see that the measurements are compatible with standard model prediction with a p-value about 77%. And due to final categorization, the results are still statistically limited. And slide 11 is about the A2 gamma analysis. This analysis have fairly high branch ratio with regard to the A2ZZ to 4 lepton channel. It also with a fairly final SOB ratio, and the final series can be fully reconstructed, and also with good resolution. And also this channel uses the Forslund dataset, and the signal are diphotons, and the background are standard model diphoton production or gamma projects or digest process. And on the right is the result. And on the top is the S+B model fit for categories, and on the bottom is the residual plots after separating the background, and we can see clean picture here about 125 GV. And slide 12 is about the cross-section measurement for the 5 main production modes. And we can see that the measurement have good agreement with the standard model prediction for the GGF plus BBH and TTH plus TH. And for the VBF, it's about 1.4 sigma higher than the standard model prediction. And the combined cross-section for the WH and ZH is consistent with standard model prediction. And here at least the number left is the method, right is the standard model prediction. And for the inclusive A2 gamma protein cross-section, at least here, and they are good agreement with standard model prediction. And slide 13 is ITS measurement in A2 gamma. And due to more studies with Forslund data set, so final binning can be done. Finally, the cross-sections of about 27 ITS strings are measured. And this first attempt to measure TTs differentially. And in general, the agreement between the measurement and the standard model is reasonable. And due to final categorization, the measurement are still statistically limited. And slide 14 is about the differential and the fiducial cross-section. First, you need to define a fiducial volume, which is restricted to phase space used for cross-section measurement. And here I give the fiducial cross-section definition. And in this fiducial volume, we can measure the inclusive fiducial cross-section and the differential cross-section. And for the differential cross-section, we can measure the cross-section as a function of its PD, number of jets, and so on. And slide 15 is the inclusive and differential cross-section in the Z2 for lepton. And this channel, can provide a resilient resolution for Higgs kilometer variables. And by fitting for lepton distribution in its final states, the differential bins to extract the measured cross-section. And on the top middle plot, we can see the fiducial cross-section. Left is by using different final states, and the middle is the mixing channel result, and the right is the total cross-section results. And for the inclusive fiducial cross-section are listed here, and they are compatible with standard model prediction. And the measurement have precision at about 10% level. And from this plot, we can see that the measurement have good agreement with the LHC cross-section working group prediction. And on the bottom is the differential cross-section as a function of PD Higgs on the left. For the low PD Higgs, which can test the coupling to B and C quark, and high PD can test the BSM. And on the middle plot is the cross-section measurement as a function of Higgs rapidity, which can test the Coulomb PDFs. On the right is the imaginary mass of leading lepton pair, and versus sub-leading lepton pairs, which is specific to A2Z channel, which are sensitive to BSM physics. And the measured cross-section in good agreement with standard model prediction. And but you can see that the results are still limited by statistical uncertainty. And slide 18 is the inclusive and differential cross-section measurement in the A2 gamma channel. And we know that we have a salient promise of photon recontrasting and identification. So we have good resolution for Higgs variables. The A2 gamma signal yields are extracted from feed to diphoton invariant mass distribution. And on the right, I give the inclusive fiducial cross-section, and they are compatible with standard model prediction. And the measurement have precision at about 11% level. And on the bottom is the differential cross-section. Left is for the PD Higgs, middle is for the number of jets, and the right is for the Higgs rapidity. And we can see that the measured cross-section in good agreement with standard model prediction, and still limited by statistical uncertainty. And slide 17 is the summary. A2ZZ, A2 gamma, and A2 WW channels are investigated with Forslund data. And the inclusive ITS and the differential cross-section measurements are presented, and all the measurements are in good agreement with standard model prediction, and sent to the increased studies with Forslund data set more finely grained measurement are presented. And that's all. Thank you.
Great. Thank you very much for summarizing these nice results. Are there any questions? Please raise your hands. Maybe I will ask just one question while seeing if anyone else has a question. Just out of curiosity, on slide 4 for the mass measurement. So you mentioned that the final state radiation photons are included in the mass computation. Actually, do you know what is the bias if no attempt is made to recover the detector level, this FSR photons?
As I know that if we consider this part in the mass computation, and the resolution can improve about 1%, if I remember correctly.
How many? Can you say that again? How much?
1%.
1%. Okay.
Yeah. The first is have it's about 70%. The first case, the kinematic fit can improve the resolution. It's the main improvement.
Okay, I see. Thank you. Okay, any other questions? If not, thank you again for this really nice summary. And we go next to Mattia Lizzo, who will tell us about recent HiggsWW results now using CMS data. Mattia, can you please go ahead and share your slides?
Hi, can you hear me?
Yeah, we can hear you.
Okay, I'll try to share my screen then. Okay. Can you see it?
Yeah, I can see it.
Okay, great.
Please go ahead.
Okay, so hello everyone. So as I already said in this talk, I'm going to present you recent HiggsWW results using CMS data and focusing in particular on the last 2 analyses published by the CMS collaboration on this topic. Oh, it's not moving on. Okay. So why is the HiggsWW channel? This decay channel has already been told. It's particularly suitable for measuring rare Higgs production modes and performing differential cross-section measurements. As you can see, the figure on the bottom, this has the second most probable branching ratio, and when compared to other decay channels, it has a relatively low background contamination. Several Higgs boson properties in this channel have been extensively studied with partial run-2 CMS results. And today I'm going to talk about 2 new results that have been performed with a full run-2 CMS dataset. So the first one is a measurement of the Higgs boson production in association with either a WZ boson, and the other one is the differential cross-section measurements of the Higgs boson production. So I'll start with the VH electronic analysis. So as I mentioned, this analysis targets the VH production mode, which is also known as Higgs run, where only associated vector bosons decay electronically are considered. So for the extreme rarity of this channel, the analysis benefits from the usage of the full run-2 CMS dataset, which correspond to an integrated luminosity of 137 inverse femtable. But the error on this measurement is still dominated by the statistical component. So here we consider 4 final states depending on the production mode and the number of leptons and jets in the final state. And we quote 2 results. One is the inclusive cross-section given as a signal strength modifier, and the other one is the cross-section in the SDXS framework. So the background contamination strongly depends on the considered final state, but the main production mechanisms are diboson processes such as WZ, Z gamma, and ZZ, which are directly measuring data through dedicated control regions embedded in the likelihood as a single bin. We also have some backgrounds coming from non-prop leptons, and they are also estimated from data by applying a transference function to loose leptons that do not pass the tight isolation and identification criteria of the analysis. Such events mainly originate from leptonic decays of heavy hydrogens that travels along the detector and produce secondary vertices. And these are primarily due to W plus jets events in the 2 leptons channel Z plus jets event in the 3 leptons channel, and they are instead negligible in the 4 leptons channel. Other minor backgrounds are instead estimated via Monte Carlo simulation. Okay, so this is the analysis strategy. We have 4 different categories. Each of them has been further split in order to increase the sensitivity to the signal. The WH same sign, we require the 2 leptons to have the same charge in order to suppress events coming from the from the Z boson production. In the WH3L channel, all the W bosons produced decay leptonically, and we apply some cuts on the dilepton and the 3 lepton mass, and similarly in the ZH3L channel, we have also 3 leptons, but 2 of them are required to be around the peak of the Z boson. And finally, in the ZH4L channel, we have 2 lepton pairs. So one comes from the associated Z boson, and the other 2 are assigned to the 2 W bosons produced by the Higgs decay. So this is how we perform the signal extraction. In the WH same sign, we have 4 subcategories where we look for E-mu final states in association with either 1 or 2 jets. And here we fit this M tilde distribution, which serves basically as our proxy of the Higgs mass itself. Similarly, in the ZH3L channel, we fit to data the transverse mass of the 2 W bosons. And on the other hand, for the WH3L and ZH4L categories, we develop we use an MVA approach by training 2 different BDT algorithms. 2 BDT algorithm in each of these categories. So the discriminant that we obtain in the end has a really good discrimination power between signal and backgrounds. Okay, in addition to the inclusive measurement, we also perform we also quote the STXS cross-section. So the purpose of this framework is to provide predefined kinematic mean square to measure the Higgs production modes. The STXS framework for the VH electronic production provides 3 macrobeams, which are divided by the transverse moment of the associated vector boson, and further split by the jet multiplicity of the final state. However, due to the limited statistical power of this channel, in our analysis, we only consider 2 beams. So we merged all jet beams, and we only consider the beam with a PTV less than 150 GV and higher than 150 GV. The fit procedure used to extract the STXS cross-section is the same as the one used in the inclusive measurement. So we can move on to the results for the inclusive cross-section. So the signal strength modifier has been extracted by a simultaneous fit to all the categories in the analysis. The fit assumes that the relative rates of the different Higgs bosons production mechanisms are as the standard model ones. So here on the bottom right, in this red box, you can see the combined result, and where the uncertainty has been broken down in a statistical, experimental, and theoretical component. And you can see how the statistical error is the dominating one. We also perform an additional fit by scaling the signal process with a different signal strength modifier in each category. So as you can see here in this figure. And we observed a slight excess in data, especially in the ZH3L category, but the measurement is consistent with within the standard model prediction, with the standard model prediction within 2 sigma. Likewise, we did the same for the STXS measurement. So here we quote 2 signal strength, 1 per STXS beam. And again, we have a slight excess here in data. And when combined these 2 measurements, we obtain a value that is consistent with the one obtained for the inclusive measurement. And similarly, we also perform a fit where we scale in each STXS beam separately each production mode. And these are the results for both the signal strengths and the measured and expected significance. Okay, so now I'll talk about the differential cross-section measurement. So this is this kind of measurements are really important for the Higgs boson, because they can be predicted with a very high theoretical precision. So in this analysis, we perform a measurement of the cross section as a function of the transverse momentum of the Higgs boson and the number of jets in the final state. So these two variables are referred to as the differential basis observable. And the nice thing is that the Higgs WW channel has enough statistics to tackle the main production mechanisms. So this analysis have been performed in the fully leptonic final state, which is one of the cleanest channels where to detect the Higgs signal. Indeed, we look for two isolated leptons with opposite charge and different flavor, and this is done in order to suppress Drellian contribution. In this channel, the leptons are emitted close to each other because of the spin correlation with the Higgs boson. And we have a pretty large signal lead with a relatively low, low background contamination. But on the other hand, the two escaping neutrinos cause the presence of some transverse missing energy, which in the end does not allow us to reconstruct the Higgs mass. So these are the production modes that we target in our analysis. Okay, so the following are the backgrounds of the analysis. The dominating one is the TT bar per production for its very large cross section. And for this reason, we apply a B veto in the signal region. There is also some contamination coming from WW per production produced by non-resonant diagrams. Although this is an irreducible background, the leptons in the final state have a really different kinematics with respect to those coming from the Higgs signal. There is also a residual contribution coming from the Drellian, and this happened when the Z decay into 2 taus that might subsequently decay into a different flavored lepton pair. And finally, there is also some contamination coming from non-prop leptons, which mainly comes from W plus jets events. And this is estimated in the same way as we did in the VH analysis. So all of these background normalizations are estimated directly from data. So this is the analysis strategy. We apply a pre-selection on our events, and those are further, and we apply further cuts on top of that in order to decrease the number of backgrounds that I just show you. And the signal region is further split in 2 categories, divided by the transverse momentum of the second lepton and also by the flavor composition of the final state. So what happens is that here we have less background contamination because we have more W plus jets event, but less TT bar and WW per production. And the overall effect is that here we have a more favorable signal to background ratio, because the Higgs signal is expected to evenly populate these 2 regions. This is the binding choice for the differential basis observable. Since for high bins we have a low statistical power, we merged some of these categories together. Okay, so these are the post-fit distributions. So in this analysis, we fit a 2D template built out of the dilepton mass and the transverse mass of the 2 W bosons. So what you are seeing here is the MLL distribution integrated over the transverse mass in each bin of the differential basis observable. And in the ratio and the smaller boxes, you can see the distribution with the background subtraction. The Higgs signal is then measured and unfolded in a fiducial phase space, which is defined with a similar selection as the one of the signal region. Okay, so these are the correlation matrices that we got from the fit procedure. So this is the one for the correlation matrix for each signal strength in each bin of the differential basis observable. So on the bottom right, you can see the correlation parameters without apply a regularization procedure. And on the top left, instead, we apply the regularization term. And this is embedded within the likelihood function as a with this expression, which is basically a penalty on any changes in the second derivatives of the parameters themselves. This delta parameter is what regulates the regularization strength. This has been obtained by minimizing the mean of the global correlation coefficient. On the other hand, we did not apply this procedure on the NZ distributions. This is a discrete variable. So here you can see the unfolded distributions for the two different cross sections. So the filler histogram is the nominal standard model prediction, while the dark green dashed line is the alternative model that we use to predict our data. And finally, on the ratio plot, you can see the relative Higgs contribution in each bin of the differential basis observed. And what we got in the end is that the fiducial cross section is 86.5 plus or minus 9.5 femtobarn, which is consistent with the standard model prediction. So this brings me to my conclusion. The Higgs WWDK channel led to really important results using run-2 CMS data, and we measured the Higgs boson production in association with either a W or Z boson, putting both the inclusive cross-section and the STXS measurement. Results are consistent with the standard model predictions within 2 sigma. We also made 2 differential measurements with respect to the Higgs transverse momentum and the number of jets in the final state, embedding the regularized unfolding procedure within the likelihood, and we observed no deviations from the standard model values. More analysis are still ongoing, and brand new results with a full run-2 CMS data are expected to give even more insight on the Higgs boson properties in this journal. Thanks for your attention.
Thank you very much, Mattia, for the nice summary of the Higgs WW results from CMS. Are there questions? Please raise your hand or go ahead. I actually had one very, let's say, technical question. I was wondering, especially on slide 17 and 18, when you went a little bit into details also for the unfolding procedure. I was wondering about the binning, whether this was, let's say, a priori already defined in the Higgs combination group, or you somehow also especially for Higgs WW with high statistics, you also optimized the binning here based on what, I guess, yeah.
Okay, I'm not sure about this, but I think we used some predefined bin. I mean, I think those are really similar from the bin for the PTH. I mean, is similar as the one used for the STXS measurement. Okay. I mean, in the STXS framework.
Okay, I see. So this is already defined by.
But I'm not sure on this. Maybe it has been further optimized for this channel.
Any other questions or comments? If not, let's thank you, Mattia, again.
Thank you.
Nice talk.
Thank you.
Okay, now we go to Matthew Forslund and he will tell us about the summation for TQH production. Matthew, can you please share your slides? You're already doing it.
Okay. Can you see the slides and hear me?
Yeah, well, we can both hear you and see your slides.
Great. Okay.
Please go ahead.
Okay. Thank you. So first off, I just want to mention that this work is based on this preprint, which is submit for publication that I listed at the bottom here if you're interested in more details for anything that I mentioned in the talk here. Okay. So we're applying soft gluon resummation to this process TQH. So I want to first describe as brief of an overview as I can of what soft gluon resummation actually is and its applications in the past. So for 2-to-2 processes, I've summarized a little bit here. Basically, incomplete cancellations of infrared divergences from virtual and real emission of soft gluons lead to these corrections. And for 2-to-2 top-quark processes, they've been shown in the past to often dominate the full QCD corrections. And so as a result, they can be thought of as excellent approximations to the full exact corrections. Some of the processes for which that's been seen in the past are single top S and T channel, TW, TT bar, some beyond the standard model processes as well, like charged Higgs production, or flavor changing neutral current processes like T gamma, TZ, TZ prime. TW and TZ prime, my collaborator is actually giving a talk on those tomorrow if you're further interested in these things. But basically, you get corrections in terms of a threshold variable, as we call it, which we define in this way. We call it S4 equals ST plus U minus the momentum squared of the final states. These Mandelstam invariants are defined with respect to the top quark. And I write the momentum squared instead of the mass squared for reasons which will become clear soon. But the meaning of this threshold variable is it's basically the extra energy caused by this soft gluon emission. It's the energy of that soft gluon. So you could show that you can rewrite this as the invariant mass of the second final state particle plus the soft gluon squared minus just the second particle squared. So the meaning is fairly clear. It's the extra energy of that soft gluon. And as you approach protonic threshold, where you barely have enough energy for the process to occur in the first place, of course, S4 goes to 0. For a review over these things, I linked a good paper at the bottom here. So these corrections involve what are called logarithmic plus distributions, which I give the definition for here, where S4 is that threshold variable. N is the order for your corrections. So if you're looking at like a next to leading order, then that would mean the highest order plus distribution would be log cubed. And then you would have all of the terms below that all the way down to k equals 0. We resum these corrections to a fixed order to a specific accuracy, which we abbreviate as NLL or NNLL, which is next to leading log or next to leading log. At NLL, you need what are called one loop soft anomalous dimensions, where soft anomalous dimensions are basically these matrices describing the soft gluon emission. They control the renormalization group evolution of the soft function and the factorized cross section. But they're one of the key ingredients for applying soft gluon resummation for a process. And you need the same order at each logarithmic accuracy. It's worth mentioning that the current state of the art is 3 loop soft anomalous dimensions. And there's a talk on those on Thursday, actually. So I started with 2-to-2 processes because that's what's been done in the past, but our formalism for calculating these things was recently extended to arbitrary final state particles in the paper, which I linked at the bottom. But the general way that they work is basically the same. We generalize the threshold variable in the following way, where we define those Mandelstam invariants with respect to the top quark in the exact same way as before. But now this second momentum squared is actually the invariant mass of all of the final state particles other than the top quark. And so in this way, it has the exact same physical meaning of the extra energy of the soft gluon emission. The general form of the corrections remains the same. The factorized cross-section form remains the same, but the soft anomalous dimensions they're process dependent, so they're going to be a little bit different when you're going to in final state particles, depending on the color structure of it and so on. But the general way of getting the corrections remains the same, of course, with modified generalized kinematics, because they're much more complicated for more final state particles. But the main point here is that TQH production is our first application to processes beyond 2-to-2 in this single particle inclusive kinematics formalism. It's worth mentioning that in another formalism, which they call 3-particle invariant mass, kinematics. They have looked at TTX production, where that's like a Higgs or a W boson. So that has been studied, but this is the first time in a single particle inclusive kinematics. So here's the process that we're looking at in more detail. So we're only interested in the T channel diagrams for this process because the S channel are much, much smaller, on the order of 10% or less in terms of a magnitude for the cross section. So we're only looking at T channel for the moment. The left diagram, you have the vector boson fusion diagram, and then on the right, you have the Higgs being radiated off a top quark. So obviously the Higgs is coupling either directly to the bosons or to the top Yukawa. And the cross section is fairly small. It's on the order of about 100 femtobarms in total at 14 TeV. And the reason for that is because of interference between the diagrams, suppressing the cross section. This interference in certain beyond the standard models, models can be changed and can enhance the cross section. So robust theoretical predictions are necessary for if we get an accurate measurement of this in colliders to see if we're actually seeing a deviation from prediction. Now, a good question one might have at this point is, why are we looking at TQH instead of, say, like TT bar H? Well, the main reason is because it's a much simpler process. You only have the two diagrams here, and you have a massless final state Q prime, which simplifies the kinematics a fair amount. And then the diagrams here are very similar to T channel single top, and soft glowing corrections for T channel single top in 2-2 were one of the processes where it was shown that they were an excellent approximation to the full results. So the hope is that this process also yields pretty good approximation to the complete next leading order results. So the explicit form of the corrections looks like this at NLO, where on the left side you have the differential partonic cross-section, where those are the Mandelstam variables I mentioned before. On the right-hand side, F leading order is the leading order differential cross-section. You have the strong coupling in front here. CF is, of course, the color factor. And then these are the plus distributions that I described before. C1 and C2 are much more complicated. They involve kinematic variables, various Mandelstams in terms of the different particles in the final state and initial state, and as well as the renormalization and factorization scales. They enter into those coefficients. The soft anomalous dimensions enter into C2 here. Then we also compute at next to leading order soft corrections at next to leading logarithmic accuracy, which are much more complicated. They would take up essentially the whole slide here, so I don't show them, but they're much more complicated. We do next to leading logarithmic accuracy because if you go beyond that, you need more than just the two loop soft anomalous dimensions. In particular, if you want the exact results, you need to have the full analytic form of the exact next to leading order results in order to match terms. And since we don't have those, we keep it at next to leading log here. In the plots that I'll show you in a moment, we got the complete next to leading order corrections for MadGraph. And then just notationally, we call ANLO the leading order plus the soft next leading order corrections, or ANNLO is the exact next leading order plus our soft second order corrections. Okay. So here's the total cross section as a function of energy that we have. So the black is, of course, the leading order prediction, and then blue is the exact next to leading order prediction. And in green here, the middle line is the approximate next to leading order soft corrections, which is just our soft corrections added onto the leading order result. And as you can see at 8 TeV or even up to like 9 TeV, the results are actually in very close agreement to the exact results using our approximation. It's on the order of like 0.01 or something that they agree. It's very, very good agreement at lower energies. At higher energies, they do deviate a little bit and they don't agree as well, but it's still fairly good. It's on the order of about 3% deviation compared to the exact results, but it's still fairly close. The deviation does get worse beyond LHC energies as you go up to 100 TeV, but they aren't necessarily expected to agree. So it's nice that they do agree pretty well for LHC energies. The second order corrections add on about a 5% enhancement for all energies in this energy range, as you can see here. Of course, this is with a central scale value, renormalization and factorization scales both set to the top quark mass. And this is with MSHT 20 PDFs, but using CT18 or any other PDFs makes no functional difference in the results. Here's the scale dependence of the cross section, where now I've dropped the A and LO results just for clarity in the plots. A good measure, or what's typically used as a measure of theoretical uncertainty, is varying the scale by a factor of 2 in each direction. Although in these plots we show a little bit larger range in the all the way up to a factor of 5 above the central scale. But as you can see, the scale variation at exact next leading order and A and NLO is reduced significantly, and the scale variation is less than 4% over the entire data range, meaning that our result is pretty stable and the theoretical uncertainty is pretty low in that. In fact, the PDF uncertainty is on the order of like 1 to 2%. So this is getting pretty, or for these PDFs, so this is getting pretty close to the PDF uncertainty even. An advantage of our formalism is we can also get differential distributions for the particles. So here I write the top quark differential distributions for rapidity and transverse momentum. This is at 13 TeV. The results at 14 TeV are very similar, though, as you might expect. And you can see that at low rapidities, close to 0, you have almost a 25% enhancement, which is lowered as you get to higher rapidities. And for PT, you have around a 25% enhancement at higher PTs at A and NLO, which is pretty significant. So these corrections need to be included if you want to make pretty accurate predictions as experimental measurements improve. So in conclusion, our updated formalism has allowed the first calculation of soft gluon corrections in single particle inclusive kinematics for a 2 to 3 process. Every process looked at before today was always 2 to 2. In particular, it still continues to yield pretty good approximations to exact results at LHC energies. It's not as good at 13 and 14 TeV, but it's exceptional at 8 TeV in particular. The second order soft corrections are still pretty significant, on the order of a 5% enhancement over the next leading order results. And we foresee many more possible applications to other 2 to 3 processes like TTH or anything else. So thank you.
Right. Thank you, Matthew. Are there any questions to Matthew? Nancy, please go ahead.
Yes, hello, can you hear me?
Yeah, I can hear you.
Thank you. Thank you, Matthew, for your very nice talk. So sorry, I got disconnected for a second, so sorry if you have mentioned it already. I was wondering if you have checked the PDF dependence on these results, like because I saw you used MSHT 20, if you have checked another one.
Yeah, we looked at CT18 PDFs as well, and the results are functionally exactly the same. We present the MSHT 20 because the PDF uncertainties are the lowest for it.
Okay, thank you.
Mm-hmm. Thank you, Nancy. Any other questions? Actually, I had one question. Maybe on slide 5, you mentioned the interference, that it needs robust theoretical predictions. Here you mean it's not easy to get the predictions in your formalism for the interference, or
No, I just mean this is justification for looking at this process, right? Because basically the interference between these two diagrams is what suppresses the cross section. And what I mean here is that certain BSM models will change that interference and enhance the magnitude of the cross section. So if that enhancement ends up being on the order of 5% or something when you're in experiment, well, that can also be accounted for by higher order QCD corrections. And so that's kind of motivation for getting higher and higher orders. That's all I meant by that.
Okay, I see, thanks. All right, I think we have, since we have a couple of more minutes, maybe I'll ask one more question on the next slide. And this is kind of coming from a naive experimentalist. In terms of this, what you call ANLO or well, let's say soft NLO corrections. I'm familiar with the, like Drelian predictions with resum calculations to an NLL or an NLL, as you are mentioning here. Is this essentially what is the relation of soft NLO to the NLL? That part it wasn't clear to me.
So NLL they're fixed order corrections, and basically the logarithmic accuracy of your corrections is separate from the order of the corrections, and so it's two different things. So in NLL, or if you went beyond this to next deleting log, you would need the two loop anomalous dimensions. You would need to match to the exact next deleting order analytic form. There's much more terms that come into it. So it's just it's a different expansion, basically.
I see. Okay.
I hope that makes sense.
Okay, yeah, thank you. All right, if there are no other questions to Matthew, thanks again, Matthew, for the nice talk. And we can move on to the last contribution to our session today. For this first session, we go to Bianca now, who will tell us about combined Higgs boson measurements at the Atlas experiment.
Can you see my screen?
Yeah, I can already see your screen.
Okay, great. So I'm Bianca, speaking on behalf of the Atlas collaboration about our combined Higgs boson measurements. So as you've seen, we have many analyses that target different production modes and decay channels, but in physics, there's lots of quantities for the Higgs boson that are independent of these, like the GGH cross-section or the PTH of the Higgs. So it's important that we do statistical combinations of all of our measurements to get the best precision and limits on these important parameters so that we can probe the standard model. And that's kind of the topic of today's presentation, shown using the updated full run 2 data sets as the input for some of these combinations. So today I'll be focusing on the coupling combinations, specifically the global signal strength, the production mode cross-sections and branching ratios, and the simplified template cross-section results, as well as their interpretations, where I'll focus on the kappa framework and EFT. For a differential, we do have one result as well for the PTH combination using the full run 2 ZZ and gamma-gamma data sets. So starting off with couplings, so this table summarizes the different decay channels that go into the combinations that I'll talk about. So far, as you can see, we have ZZ, gamma, gamma, and VHBB at the full run 2 data set, and these are the only results used for the SDXX combination, as well as the EFT interpretation done on top of that. We do also have the Higgs to mu mu and Higgs to invisible at the full run 2 data set, and these are used for some of the kappa framework results. If you want more information of all these analyses, I've linked the conference notes or the publications here. As far as how we actually do combination, we do a product of the likelihood functions, and every time we have systematics from the same source, we correlate them. But moving straight to the results and starting off with the global signal strengths, or mu. So this is defined as the cross-section times branching ratio, normalized the standard model expectation. You can, of course, measure this in different channels, but here we simultaneously measure one parameter to all of our data. And when we do that, we have a central value of 1.06, and you can see the negative log likelihood scan shown in this plot here, broken down also by components. We're at the point now where systematic uncertainties dominate, and this just comes from the fact that we're working with a very large data set. To give you some idea of our largest theory uncertainties, QCD scale is about 4% on GGF, and the PDF and alpha S uncertainties are about 3% on GGF. And as a reminder, GGF is about 90% of the signal, and we predict this at N3LO already. So overall, this result is quite consistent with the standard model value of 1. And we can also do this type of measurement, but for the individual production modes. So here we fix the branching fractions to the standard model value, and we simultaneously fit to all of our data. The production modes that we measure here are GGF, VBF, WH, CH, and TTH. And you can see from the results, again, everything is very close to the standard model value. Just like for the mu results, we are coming to the point where the systematic uncertainties are the same, or they're approaching the statistical uncertainties. Another interesting point about this result is the correlation matrix, where we have actually decreased the correlation between VBF and GGF from 15% from our last publication down to 8%. And this mainly comes from our updated ZZ and gamma-gamma results. It's also the first time we have over 5 sigma observed in all of our production modes, and this is the first observation of WH with an observed significance of 6.3 sigma in this round. We can take this a step further and measure the cross-section times branching ratio. We're still statistically limited to the point that we can't measure all of them. So the ones we can't, we fix to the standard model. And most specifically for VH, we fix the fraction of ZH and WH right now, but this will become possible as we collect more data to measure them. In terms of the results we have right now in the combination, GGF is largely driven by ZZ and gamma-gamma, and VBF is driven by gamma-gamma, tau-tau, and WW, and this will improve further once we include the full run-2 data set for WW and tau-tau. And overall, we see good agreement with the standard model. So I won't go into too much detail about the SDXX scheme since other people have talked about it before, but as a reminder, it's measuring the cross-section in exclusive bins of phase space, and the full scheme is shown here on the left plot. For this combination, we are using the full run-2 ones, so ZZ, gamma-gamma, and VHBB. So we don't have the statistics to actually measure all of these bins, so we have to merge. And you can see the resulting merge scheme that is shown on the right plot. And our criteria for merging these bins is we merged anything that was very highly correlated, and we just aim to keep the uncertainties below 100% with the exception of a couple bins that are sensitive to BSM physics. So you can see from the plot on the right that the results are actually quite prolific, and we really have the ability to measure a lot of different parameters with the full run-2 data set, and I just wanted to highlight a couple from the combination. So in terms of GGH, we can measure the low PT very well in ZeroJet, as well as we've gained, I think, a bin in the high PT. The same is true for QQH from the VHBB combination, where we've gained the ability to measure more bins. This is also the first combination of differential TTH production, and it's the first combination of TH. Even though these are largely driven by gamma-gamma, the ZZ does contribute and help this a little bit. One thing to point out here is that there's a very large correlation between VH and the branching ratio BB. And this is just because both the sensitivity for both of these come from VHBB, and this will go down as other channels begin to catch up. Overall, at a glance and from the p-value, you can see that there's good agreement with the standard model overall and no significant deviations. So moving on to the interpretations and starting with the kappa framework. So this is using kappa factors and applying them to the standard model cross sections and branching ratios. And we do this so that we can constrain the coupling of the Higgs boson to other particles. So there's two kind of ways to do this. I've given the example for gamma-gamma shown here. So you can have effective couplings like the kappa gluon and kappa gamma shown here, or you can put them onto standard model vertices like the kappa top here. The Higgs width can also be affected kind of by two things. One is invisible decays. So this is things like Higgs to ZZ goes to 4 neutrinos, and we can identify these by large ET miss signatures. And the other thing that can affect the width is undetected decay. So these are final states that we're not sensitive to in our analyses right now, like light quarks or BSM particles that don't have a sizable EFT. There's another full combination that has recently come out from Atlas on just Higgs to invisible results, along with some interpretations that I've linked here because I won't have time to go through it, but you can see there's a 15% improvement on just the run-2 VBF only analysis, which is exciting. So starting off with the simplest assumption, so where we assume no new physics in the loops or modifications to the Higgs total width, we can fit kappa for WZ, top, bottom, tau, and muon. And kappa muon is especially exciting because it's no longer a limit like it was in the previous publication, now that we've updated to using the full Run2 data set for the Higgs to mu analysis. It's also quite impressive to see that we have really good agreement with the standard model, even over 3 orders of magnitude for the particle masses. Another way to probe the standard model is to look at the coupling strength of the gauge bosons to the fermions. So this would be equating kappa W and kappa Z to kappa V, and the same kind of story for the fermions. Here we don't assume any invisible or undetected decays, and you can see that we agree really well with the standard model, which is at 1,1. We can also do this for BSM contributions to loops. So this is looking at the effective couplings that I was talking about before for kappa gluon and kappa gamma, which can show any new physics originating in loops. We do this under 2 assumptions. One is assuming more standard models. So this is a plot shown on the left where we fix BU and BI to the standard model value of 0. And you can see the contours as well as the best fit showing we are consistent with the standard model. And the second version of this is loosening this assumption and actually letting BU and BI float free. And you can see the corresponding result from the right panel of this plot, along with the limits on these values at the 95% confidence level. Lastly, we can do a generic parameterization and fit all of the coupling strength modifiers at once, again, under the same 2 assumptions. So the left panel is assuming BU and BI are standard model-like, and you can see everything is quite in line with the standard model expectation of 1. And the second scenario is letting those parameters float free, but here we have to assume kappa V is less than or equal to 1 in order to constrain the undetected branching ratio. What's really exciting about this round of results is that we were able to exclude negative kappa top values at 2.7 sigma when we assume there's no BSM contributions to the total width. So the kappa framework is very useful, but it does have several limitations, one being that it's at leading order and it's also missing the differential information that we measure. So this motivates us to use other frameworks like EFT or more model-specific ones like the Higgs doublet or the minimal supersymmetric, which I've included the latest results in the backup plots if people are interested. So as a quick recap of standard model effective field theory, it's a model-independent way to parameterize the effects of BSM, and we do so by adding higher dimension operators. In this case, we care about the ones that respect standard model symmetry, so that would be the dimension 6 and dimension 8 operators. And just like before, we use our cross-section measurements to try and constrain, in this case, the Wilson coefficients, and we do this at a fixed energy scale chosen to be 1 TeV. For this analysis, we only consider dimension 6 operators, and we use the commonly used Warsaw basis. These interpretations were done using the STX results that I showed previously in this talk. And as always, the goal is to probe as many parameters as you possibly can. So this was done systematically by taking the STXX basis and rotating it into the EFT basis, and then performing an eigenvector decomposition to determine which operators or which combinations of operators we're actually sensitive to given the data set that we currently have. And that's what this matrix plot is actually showing you, is the ones that were chosen to be measured with the current data set. So moving straight to the results, so when you square the matrix element from the D6 operators, you have the linear term suppressed by 1 over scale to the power of 2, and the quadratic term suppressed by 1 over scale to the power of 4. We parameterize the cross-section and branching ratio using the linear terms shown in the blue, as well as the linear and quadratic terms shown in the orange. And for the quadratic terms, we don't consider interference with D8 operators, even though they come in at the same 1 over lambda to the 4 power. So you can see from these results that it does seem that adding in the quadratic gives you an additional constraint, even though you end up with a second minimum in one of the parameters. But overall, there is a non-negligible influence from including taking these into consideration. However, overall, the results are compatible with the standard model in both kind of ways, and there's a lot more details on this combination that I don't have time to go through, so I've relinked the note. The last combination that I just want to touch upon is differential. So looking at differential observables is another great way to probe the standard model because it's very model independent. PTH is especially interesting because it can indicate new physics. If you have modifications at the low PT, it can be indicative of modified light core coupling. And if you see modifications at the high PT, it could show new BSM particles in the GGF loop. So for this combination, we used the full run 2 gamma gamma and ZZ results, and you can see the combined value by the black and the expected with the histogram behind it. So overall, the results were compatible with a p-value of 78%, and the plan is as well to add in more results as they become available, and also to perform combinations on other observables. So to conclude, for couplings, we've been able to include the full run 2 analyses that were available, and we've increased our precision on the signal strength, production modes, branching ratios. We've also been able to extend the phase space that we can measure in STXX when combining all of these, and perform some nice combinations on top of that, none of which showed any deviations from the standard model. For differential, we've done the combination on the PTH observable as well as the cross sections, which I just showed the one for the energy scale here, which is always nice to see the agreement as a function of the center of mass energy. And perhaps the most exciting thing is the outlook of what's yet to come. So as more results become available, they'll be added to the combination. The most recent has been Higgs to WW, which I've linked there. And of course, all of these additional channels bring precision in different regions of phase space, improving our knowledge of the standard model. So there's lots of ongoing work in the combination world for different observables as well as interpretations yet to come. Thanks.
Thank you very much, Bianca, for this very clear talk. Are there questions, comments? Okay, maybe it was very clear. Actually, one maybe just a question, and this is just me wondering, as far as the Higgs couplings to charm quarks is concerned, so in a sense that those results, let's say with more and more statistics, let's say the approach would be at one point to include them in these combinations, correct? So when would you expect full run 2 results from let's say Atlas or CMS, in a sense that when do you think they would be, let's say, precise in a way, in a state that they can be used in the combination, or perhaps that comes for highly Lumiere LHC and it's the precision will not be good enough for LHC?
Oh, I'm not too sure on the timeline for the direct searches. The one thing I know is that we have put out the interpretations on PTH, at least from ZZ, but as far as direct searches, I'm not super sure when those will come out, especially not from CMS.
Okay, sure. Any other questions to Bianca? All right, if not, thanks again, Bianca.
Thank you.
And since this was the last contribution of this session, let's thank again to all the speakers and for more or less also staying on time as we've managed to finish the session a few minutes before. So just to say that our next session for our working group will start today at noon, so at New York time. So hopefully we will see you all there. Other than that, yeah, thanks again, and see you in a bit.
Okay, I'll set a timer.
So say that again.
I'll set a clock here at noon. Okay. in the display.
Yep, thank you. Sounds good.